to example 2, we have the owners of some rental car company that have determined that if they charge a price of P dollars per day to rent a car, where P is constrained to be between $50 and $200, then the number of cars in that they rent per day is given by this linear function of P. So in other words, the number of cars that they rent is going to be 1,000 minus 5 times the price that they charge. And we're told that if they charge $50 per day or less, then they'll rent all of their cars. If they charge $200 per day or more, they won't rent any cars. And now, assuming that the owners plan to charge an amount between these two boundary amounts, how much should they charge to maximize their revenue? So it's usually a good idea in these optimization problems to start by just identifying what it is that you're trying to find. In this case, that's how much they should charge. So we're trying to find P in order to maximize their revenue. So P is the thing that we're trying to find, and we're trying to maximize R, the revenue. So usually it's a good idea to express the thing that you want to maximize as a function of the thing that you want to find. So I'm going to try to maximize the revenue as a function of the price. Remember that the revenue is just equal to the price times the quantity sold, or in this case, I guess the quantity rented. Now, because I want this to just be a function of the price, I can use P as my variable here. P represents the price, and then I want to multiply by the quantity that we sell. But in this case, we're told in the prompt that the quantity sold is equal to 1,000 minus 5P. So this will be 1,000 minus 5P. So this is what we want to maximize. Usually I like to distribute here, so I would distribute the P. Otherwise you have to use the product rule whenever you start taking derivatives, and I normally think it's a little easier to just distribute right away. So, but it's sort of a matter of personal preference, you can do either. If you do distribute, you'll get that the revenue function is 1,000 times the price minus 5 times the price squared. So this is what we want to be maximizing. And in order to maximize this function, we'll turn to the first and second derivative tests. So we'll compute the derivatives here. Now we're taking the derivative with respect to P. So R prime would just be 1,000 minus 10P. And our double prime, if you want to compute it right away, you can, will end up being a negative 10. Notice that this is a negative number, and therefore the concavity is negative or downward for this revenue function. So that means that if we were to plot the revenue function as a function of P, it would look something like this. And what we're looking for is the place here, this price P, where the revenue function attains its maximal value. So we're trying to maximize the revenue here. And the way that we're going to do that is through this first derivative test, we look for the critical points. Remember that the critical points are the places where the first derivative equals 0. So if you don't have a picture, what you do is you take that first derivative and you just set it equal to 0. And then you solve for the critical point algebraically. So here we would get that first derivative, 1,000 minus 10p equals 0. And then rearranging this to solve for p, you'll get a p-value of 100. So this is our only critical point. And as we've already seen, because the concavity is downward, we're looking at a picture like this, where the critical point that we just found, which is 100, is sitting here at a critical value with negative concavity, and therefore we're looking at a local max. So this represents a local max. It's not necessarily the absolute max. So there's something that I want to mention about this particular problem, which is that in this problem we have these two boundaries. We have 50 and 200. So our price is constrained so that it does not go below 50 and so that it doesn't go above 200. Whenever you have boundaries like this, it's possible that the maximal value for the revenue is going to occur at one of these boundary points. So you should basically treat these boundary points as if they were critical points. So they're not necessarily critical points, but the maximum can still occur at a boundary point. So we really have three candidates for our maximal revenue, or really I should say the price that maximizes revenue. The three candidates are 100, 50, and 200. So we need to see which one of these 3 points is actually the one that maximizes the revenue. And in order to do that, what we can do is we can just plug in all 3 of those points. So I want to know what is the revenue whenever we set the price at $50, what is the revenue whenever we set the price at $100, and what is the revenue when we set the price at $200. Because any one of these could represent the maximum. Now, we've been told that if they set the price at $200, then nobody rents, so this revenue would just be 0. And then to figure out these other 2 revenues, all that we're going to do is we're going to plug in 50 or 100 into the revenue function, which we found up here. So if I plug in 50, what I get is 1,000 times 50 minus 5 times 50 squared. And if I plug in 100, I get 1,000 times 100 minus 5 times 100 squared. So I'm just plugging in both of those values into this revenue function that we found up here. And if you plug these into a calculator, what you'll end up getting is that the revenue, if you set the price at $50 per day, is $37,500. And the revenue, if you set the price at $100 per day, is $50,000. So from these 3 candidate prices, what we see is that the maximal revenue that we can get from these 3 candidates is this 50 grand. So that's going to be the maximal revenue, but I think what we were looking for, let me see. So it says, assuming the owners plan to charge the customers between $50 and $200 per day, how much should they charge to maximize their revenue? So the thing that we were looking for at the end is not actually the maximal revenue, it was the price P. So the way that I would answer this question is like this. I would say they should charge $100 per day. Now, in this particular case, because the function that we were trying to maximize was a quadratic, we actually know that the graph of this function is going to look like this. So it's going to be a downward opening quadratic. And for any quadratic function, the maximum is always going to be attained, or the minimum will always be obtained at a critical point. So in this case, because the revenue function was a quadratic function, we know that the maximum will actually occur at the critical point, just because we know what the graph of a quadratic function looks like. So it would be okay in this particular problem to skip over these extraneous steps, these boundary steps, and know that the critical point is going to be the one that gives us the maximal revenue. But in general, in these kinds of problems, you do have to treat those endpoints as potential maximum. So we may have that the left endpoint or the right endpoint is actually where the maximum is attained, even if those are not critical values. So it's good to get in the habit of checking whether that left endpoint or that right endpoint is actually the one that gives the maximal revenue. But in this particular case, because we're looking at a quadratic function, the endpoint is not going to be where the maximum is attained. The endpoint will always be attained at this critical value. So either way, what we end up getting is that they should charge